I am Baher Abdulhai. I'm a professor at the University of Toronto, Civil Engineering in the Transportation Group. I'm also the director of the Intelligent Transportation Systems Center, which is where we are. Transportation is a real world, large-scale, citywide problem that has direct impact on the economy. We estimate that we're losing $6 billion a year in Ontario, and also touches on the environment with pollution, on general lifestyle. We are all stressed out in traffic and we waste quite a considerable amount of time and energy into it. But also it touches us at the household level, at the individual level. So it's a large scale problem that penetrates all the way to the individual citizens of a city. Now, what about it? What is the issue of the transportation problem? We're trying to move people and goods as fast as possible, efficiently and sustainably from origins to destination. But what we suffer from is congestion. So if there is a single word that describes what we're talking about, it is congestion. When you think about congestion methodically, like what is it? Why is it happening? As a large-scale system, you have demand, that's the number of cars that need to be moved around, and you have the capacity of the system. So in simple terms, it's demand to capacity ratio. Once demand to capacity ratio gets close to 1 or tries to exceed 1, then the system breaks down and comes to a halt, and this is what we experience every day in the form of congestion. Now the question is, what can we do about it? When you think about demand on one side and capacity on the other side, it's not rocket science that you either need to deal with demand or capacity or the interaction of the two. Dealing with the demand means make people drive less, either by taking transit, driving during off-peak period to the extent possible, or give them disincentives to be less dependent on the car and more into active transportation and sustainable modes of transportation and so on. So that's the demand side of the equation. Now, on the supply side or the capacity side, the brute force approach that we have always used for decades is build more. You fill it up, you don't have more space, then you acquire land and build further infrastructure. But this is obviously very costly economically, and in many places we run out of space. Even if we have the money, we cannot build our way out of congestion anymore. So that leaves us with how demand and supply interact. If there is friction between the two, and if we can smooth enough, really grease the wheel in a sense, to make more demand fit in the existing infrastructure capacity, then that would be also beneficial. And this falls into the umbrella of using technology, intelligent transportation systems, all kinds of communication infrastructure, computing, optimization, control, and so on. The objectives of all fall into the category of how we can use the infrastructure better in a smart, intelligent way so it can take more without breaking down and without having congestion. Right. So let's now talk about intelligent transportation systems. Think of it as an umbrella of all kinds of technologies, communication, computing technologies, to help smooth how demand fits into the existing infrastructure capacity. How can we use that? Well, I'll give you specific examples. Take traffic lights, for instance. What are they for? Traffic lights are intended to give people access to the intersection right of way with conflicting movements. Some people want to go north-south, others want to go east-west, and if you allow them all at the same time, they will simply crash. And even if they don't crash, they will crawl through the intersection, so it will be very slow and inefficient. So traffic lights are intended to organize this movement in order to enhance safety, that's number one, and also do that efficiently as possible without burning time, meaning that it happens a lot that you approach an intersection, you stop at a red light, and nobody else is using the other directions, and you're wondering, can we do better than that? So from that perspective, we can use intelligent systems, artificial intelligence based, essentially computer software, control software, that mimics how humans learn. And we put what we call an agent. That agent is a software that sits on a chip inside the intersection, It makes the traffic light learn from what it sees and learn from the consequences of its actions. So if the traffic light moves the wrong direction, for instance, then queue length will propagate very fast, and we all lose time. So it would learn that, okay, I shouldn't do that again. While on the other hand, if it flips the lights in a certain way that worked very well, everybody's happy, and queue length and delays are being reduced, and it says, that's a good thing, I should reinforce this and repeat it. And this is the concept of reinforcement learning from artificial intelligence. So we have this situation you face, you know what to do right away. You don't say, okay, I'm going to trigger my computer in my head to figure out what to do in this situation. No, you react right away with hopefully the optimal decision. So the traffic light in this case learns how to map what it sees, we call that the state of the system, to what should be done, which is actions, and guides itself using reward signal, whether things are improving or deteriorating at that intersection to enhance its operation all the time. So imagine now that you have a bunch of intersections and all of them are acting independently, intelligently. So each intersection knows what to do to reduce delay at that particular intersection. Now, let's take it a step up now and say, okay, what happens at a given intersection affects the downstream intersection and is affected by the upstream intersection. Essentially, it's a network, right? So they are all talking to each other, not directly talking, but in terms of sending traffic and congestion at each other and so on. So we add another layer using game theory that says, you guys, intelligent agents, can you talk to each other and figure a way out that would be optimal overall for the network? It's kind of like players in a team, soccer game or a hockey game. Yes, as a player, I want to score for my name and fame and so on, but at the same time, I want the team to win. So it might happen that I'm getting close to the goal, but I decide to pass the puck to somebody else who has a better chance at enhancing the game. So this is exactly what the traffic lights do. They say that, okay, maybe I should move traffic northbound, that's what's best for me, but I see that downstream people are stuck, so there is no point exacerbating the problem downstream. Maybe I will hold traffic a little bit, which is known as metering at the perimeter, meaning that prevent traffic from pouring onto a critical intersection that we know is failing. So overall, they act as a smart team of agents that optimize network-wide, like two-dimensional grid, what is happening. Each intersection talks to the 4 neighbors, and each one of the neighbors talks to the 4 neighbors, and in a cascading manner, you cover a larger area. Let's move on now to freeways. Traffic lights, we understand it's a grid system and intersections and so on, but the freeway doesn't have intersections. And people ask, why does it break down? Even my son, when he was 10 years old, he asked me, like, if the first guy in the queue moves, then everybody else would move. And you wonder about, like, why is it breaking down as such while there are no specific interruptions, accidents and incidents aside, and so on? Well, the secret here is that when you throw a lot of demand onto the freeway from the main line and on ramps and so on, simply demand exceeds capacity, which is the simple ratio. If you have the Gardner, for instance, 3 lanes can take up to, let's say, 7,000 vehicles per hour. You put at it 8,000 vehicles per hour, guess what? The difference will have to wait. And that waiting is queuing, and this is all the cars you see on Spadina and University Avenue and all the feeders onto the Gardner. Not just waiting, but they are also pushing their way onto the freeway, creating friction. So the freeway itself breaks down and capacity of that freeway drops. So instead of being able to handle, let's say, 7,000 vehicles per hour, now we're talking about 6,000 vehicles per hour, which exacerbates the problem further at the time we need it the most, which is during rush hour. So what do we do in this situation? One possibility is the so-called ramp metering, where we control the ramps with kind of similar to traffic lights, but simpler, that inject cars onto the freeway one at a time in a manner that guarantees that the main line demand as well as the on-ramp demand together don't exceed the capacity of the freeway. So that prevents breakdown, that prevents loss of capacity during the time we need the most, and enhances safety, so it's benefits all around. And we're talking about total time savings of like 20% to 40% sometimes, which is equivalent of adding another lane to the Gardner without building one. So that's another example of how you can use intelligent systems. And we use the same technology as traffic lights, which is self-learning agents, control software that is embedded on traffic lights, on the ramps, that learn how much flow should I allow per time step to keep the capacity flowing. If we, let's say, priced the Gardner, the reaction from the public, no, I'm paying taxes, I have built this with my own money, why would I pay for it again? Think of it as a way to give them more for their money, because what you will get is higher capacity. So we're not sending people home, away from the freeway, we're enabling the freeway to take on more smoothly and also save people time. Let's say, for instance, you want to come downtown at 2 o'clock in the morning. Your trip is going to be super fast, at the speed limit even higher, and you will be there, let's say, in 20 minutes, half an hour, let's say. If you do the exact same trip during rush hour, you will budget an hour and a half. So an hour and a half versus half hour. What is this extra hour? You're simply sitting in queues, agonizing about it and wondering what to do, and so on and so forth. So with that in mind, if I offer you with a little bit of payment, I'm going to shave off this hour, it might be a very sweet deal for the public. So it's a win-win situation. One, it raises funds for enhancing the infrastructure, building more transit, and so on. Two, it gives people much faster travel and less agony and congestion. Three, it helps operators, the city and the ministry and so on, run the system in an efficient manner. Now, the caveat here is that let's not be single-minded. Let's either price, or ITS. It's like a portfolio of solutions. We want to make traffic lights smarter, and believe it or not, that helps the Gardner. Like we have seen in our research that if you properly run the traffic lights around the Gardner's on-ramps and off-ramps and so on, traffic on the Gardner itself speeds up. Like all the congestion near the Spadina exit, why is it lined up? Because everybody wants to exit at Spadina, and there is a bunch of traffic lights there that holds them up, so they line up on the freeway. So you make the traffic lights better, you control the on-flow on the freeways. All are supply-intended actions that would smoothen up the capacity or enhances the capacity of the supply system. And then you have a pricing layer that would rationalize demand, the two together or everything together in a basket, that would improve things like 30–40% less congestion without building anything, without building infrastructure. All right, so let's think a bit about the cost of technology. If you want to put intelligent transportation systems on the road, whether it's for traffic lights, freeway, or whatnot, then people ask how much it's going to cost, right? So let's compare the cost of an intelligent solution versus the brute force infrastructure expansion. Think a simple case, an intersection. An intersection is breaking down, you don't have enough capacity to push people through. What should you do? One possibility is to buy land around the intersection, add a lane here, right turn lane, left turn lane, essentially expand the infrastructure. We're talking about per intersection, millions of dollars, depending on the situation and the price of the land and location and so on. It could be $5 to $10 million just to expand the intersection a tiny tad to take 30% more traffic, let's say. While you can do exactly the same effect using a smart traffic light that would cost maybe 2 or 3% of that budget. Let's say 5% of that budget. So compare $10 million to 5% of this, which is huge cost savings for society. So that's the real incentive And the reason why we're looking at technology, because it simply offers better performance at a fraction of the cost. Now, everything we talked about is daily transportation problems, meaning congestion during morning peak, congestion during after peak, at the afternoon peak. But rarely we think about emergency situations. Let's say something goes bad, severe weather conditions, man-made disaster, natural disaster, nuclear leak. Then what happens in this case? It's not just sheer demand in the sense that everybody's running to the road. The pattern of doing so is completely different from the daily patterns. Daily patterns, we live certain places, work certain places, and that repeats, and the infrastructure grows in a manner to accommodate this. Now, if we're running for our lives, that pattern changes completely. It becomes much higher demand, and where people are going to is completely different, and the infrastructure is not designed at all to accommodate this. So the end result is, if it happens, God forbid, then we'll be sitting on the road for hours. We simulated a mock scenario of something going bad in Toronto, and we found out that if you want to evacuate 2 million people out of Toronto, 2 million people, push them into the suburbs. We found out that the last person that will get out, measured from the onset of the problem, of the disaster situation, will leave the city after 30 hours. 30 hours of being on the road, like what you see in the movies. Cars parked on the road, people are eating outside the car because nothing is moving. That's days and days of congestion. Now, if again we employ technology in this case, not in the sense of only a smart traffic light, but a system, a software system, an optimization system that takes over everything and says, okay, I'm going to release people into the network, into the system in stages. This is called evacuation staging. So 2 million, I'm dealing with 2 million people, maybe I can evacuate them over the course of a few hours. But what would be the optimum ratios or percentage of releasing that demand into the network? We optimize this. And then the other question, where would you send people to? If everybody heads in the same direction, nobody will go anywhere. So we try to take the demand and spread it in all directions. Assign people to safe destinations, call it shelters, either physical shelters or simply getting out of harm's way. And when we assign people to destinations in an optimized manner, we guarantee that they get there as fast as possible and hence minimize their exposure to risk, whatever the cause of risk is. And then not only this, we tell them how to get there, meaning take this route and not that route, because it's going to take you there faster. So when you combine the 3 dimensions, that is evacuation scheduling, destination choice, as well as route choice, combined, that makes the evacuation time much, much shorter. Same problem as the mock evacuation of Toronto, where the last person got out after 30 hours. Now under the optimized system, the last person gets out after 8 hours, 7-8 hours, which is 75% reduction in evacuation time and exposure to risk. Again, we're talking about software and a computer. So it's not really, we're not double-decking all the roads or building a city underground. It's intelligence in the form of a piece of software that runs, yes, fairly complex optimization system, but the outcome of this is outstanding, given even under the assumption that 20% of the population will ignore what we say and do whatever they want. You argue, is it like 80% compliance? Is it reasonable? Maybe 70, maybe 60. Still, you'll get significant improvement compared to do nothing and run for your life scenario where nobody will get anywhere. And that takes care of vehicular traffic, meaning people who have cars and can drive them, as well as the transit captives or people who are car-less, don't have cars. Then we take over all the available buses and make them shuttle between pickup points, known pickup points, and safe destinations until you drain out the population.